Okay, good morning class. Welcome to my lesson today. My lesson is on carbon and its compound. Today I would like us now to learn about the carbon and its compound. And we are going to start by first of all talking about carbon before we go to its compound. I want us to look at now what we call carbon. Carbon is among the first 20 elements. This is one of the 20 elements we have in our periodic table, and this is one of the elements among the 20 elements we have. It's one of the elements that have a very unique property that other elements don't have, and that unique property of carbon, we are going to discuss it in our class later, but we are going to start with the carbon itself now, basing on now its position in the periodic table. I think when you are discussing about the first 20 elements, you discuss about carbon as one of the elements, and you said that carbon is number 6 in the periodic table. This is number 6 in the periodic table. Number 6 in the periodic table. And being number 6 now, carbon will have a configuration, electronic configuration of carbon is 2, 4. So these the 4 valence electron in this outermost energy level make this carbon to be in group 4. So we are saying that carbon is group 4 element, group 4 element. And I remember when you were discussing about now the groups in Form 2, the first topic, when you were discussing about the groups, you said that the groups should be written in Roman numbers, capital Roman numbers. So this is group 4 because of the 4 valence electron in the outermost energy level. It is actually found also in period 2. It is found in period 2 because it has 2 number of occupied energy levels. Now, having known this one here, we are also going to discuss this unique property that carbon possesses that other elements do not have. This unique property, we call it catenation property. So carbon has ability to catenate. This is generally what you need to understand. So we said that now in Form 3, when you're discussing about the the organic chemistry, I remember you talked about hydrocarbons. You talked about those hydrocarbons. You talked about those alkenes, those homologous group or homologous series. And I remember you bonding a carbon with another carbon. So when you look at carbon here, this carbon bonds with another carbon, and it's not easy for you to see, especially most of these elements bonding with one another, forming a very long chain. This carbon can bond to so many other carbons. This one will actually result to the formation of what we call long chain. Forms now a long chain carbon. Now, a long chain of carbon. So this ability here of actually an element bonding with itself to form a long chain is what we call catenation. Catenation now, this is actually ability of an element, to bond with itself, to form a long chain, This ability, we call it catenation, and this one is mostly found in carbon but not any other elements among the 20 elements in the periodic table. Now, having known this about carbon, Now we can go directly to what we call allotrope and allotropy. We're going to discuss something on the allotrope and the allotropy. Allotropes of carbon. Allotropes of carbon. Allotropes of carbon. Allotropes of carbon. Before we discuss about the allotropes of carbon, I would like us now to define this word. The word here is allotrope. And then there is also what we call allotropy. But before now we come to allotropy, I would like us now to discuss the word allotrope here. Allotrope actually, listen, and I want you to get this one clear because this thing is very much examinable, and most of the time students miss when it comes in an exam situation. Now, I want you to get this. So, this carbon here, which is one of the elements in the periodic table, carbon here, which is now one of the elements in the periodic table, it actually takes different form. One, it has a pure form, or the one we call it now the crystalline form. Then it also takes non-crystalline form. Now, to differentiate allotropes from non-allotropic materials or from non-allotropic compounds, we are going to actually use a keyword in defining this. There's a keyword that actually needs to be found within the definition of this word here, allotrope. And I want us now to define this word. In defining this, we can say allotrope is these different crystalline forms of an element, different crystalline forms of an element in the same physical state. Different crystalline forms of an element in the same physical state. This is the key word here, crystalline. Different crystalline forms of an element in the same physical state is what we call an allotrope. And why am I using this keyword here? I think in defining now allotrope, this keyword should be in the definition. If you are not putting this keyword here, then your definition will not be complete. We are actually differentiating a crystalline and non-crystalline forms or non-crystalline compounds. So to actually differentiate allotropes from other non-crystalline forms, we actually use this word here. So crystalline actually is the definition, it's defined as different crystalline forms of an element in the same or in that same physical state is what we call an allotrope. And now, when these forms are existing or taking different existence, or when these different forms we are talking about here, when they exist differently, then the word now becomes allotropy. So allotropy is actually existence of those different crystalline forms. Those different crystalline forms, the way they exist is now what we call allotropy. So allotropy, this is the existence, allotropy is the existence of different crystalline forms, allotropy is the existence of different crystalline forms of an element, the existence of different crystalline forms of an element in the same physical state, in the same physical state. In the same physical state, that is what we call allotropy. So these are the two major definitions that you need to understand. Now, we are going to discuss about now the allotropes of carbon. For the allotropes of carbon here, get this clear please. Allotropes of carbon. Carbon has majorly 3 allotropes. We have around 3 allotropes of carbon. We have around 3 allotropes of carbon. We have around 3 allotropes of carbon. The first one here, the one that exists as a pure form, there are only 2. That one is graphite is one of them. Diamond is another one. Graphite is one of them. Diamond is another one. Then the third one here, we have the synthetic allotropes of carbon. We call them fullerenes. Some people call it fullerenes. This one is also called Buckminster. Fullerenes is also called Buckminster. So these are the 3 allotropes of carbon: graphite, and then we have diamond is the second one. We have fullerenes. These are now the synthetic allotropes of carbon. Fullerenes is also called Buckminster. Fullerenes is also called Buckminster. So these are the 3 allotropes of carbon, and we are going to discuss this one in details, one after the other. I want us now to discuss on diamond. And for the diamond here, I'm going to draw you a structure of this diamond here. From this structure, we are going to discuss 1, 2, 3 things here. Diamond has a structure like this, drawn like this. Example, this one here is one of the carbon. This one here is another carbon. This one here is another carbon. This one is continuous. This structure repeats itself. This one is just a skeleton structure we have. This is a carbon, I want us now to look at this one here. If this is a carbon here, this is another carbon, this is another carbon, this is another carbon, this is another carbon. So each of these carbon here has been bonded to 4 other carbons. From this carbon, we have a bond here. This bond, we call it a covalent bond. One of the strongest bond we have. This one here is also a covalent bond between a carbon and carbon atom there. We have a covalent bond. We have another covalent bond here. So when you look at this one here, the covalent bond, we have a uniformity in the strength, in the strong covalent bond within the structure here. So when you look at this structure, carbon and to another carbon has been bonded together by a covalent bond. Carbon to another carbon has been bonded together by a covalent bond. Carbon to another carbon has also been bonded together by a covalent bond. Another carbon here, covalent bond. So there's a uniformity in the strength of this covalent bond here. So we can actually say from this one that now diamond, having now a covalent bond, strong covalent bond there, we can say that now is one of the hardest material, or is one of the hardest substance, or the hardest material, and some hardest material. And there's a reason behind this one. Why are we saying that this one is hard? From the structure here, we can actually come and say something on this, that now this carbon and this carbon here, we have a covalent bond. So this covalent bond is uniform. Between this carbon, we have a covalent bond. So there's that uniformity uniformity in the strength of the covalent bond throughout the structure, and because of that one, then we can actually say that diamond is one of the hardest materials. So the reason behind the hardness of this diamond here is that now due to uniformity of strong covalent bond throughout the structure. due to uniformity of strong covalent bond throughout the structure. So due to the uniformity of that strong covalent bond throughout the structure, then because of that one, we can say that this diamond is very hard. Then another property of diamond that we can actually discuss here, we can say that diamond is a clear, transparent, and shiny. Clear, transparent, and shiny. It's clear, transparent, and shiny, crystalline. It's a shiny, crystalline, transparent, clear, and shiny, crystalline. Apart from that one, very important thing here that you need to know also about this diamond, we can say that diamond, this is what we can say about diamond, that diamond has a high melting and boiling point. This is due to the strong covalent bond, due to strong covalent bond. This is due to strong covalent bond. Another one we're going to discuss here is due to strong covalent bond. Another one that we're going to discuss here about this diamond, that diamond, they are poor conductors of heat and electricity. They are poor conductors of heat and electricity. They are poor conductors of heat and electricity. Now, why are we saying that this diamond here is poor conductor of heat and electricity? The reason is that now they lack what we call delocalized electron. So here, reason behind this, we are saying it lacks delocalized electron. So due to absence of delocalized electron, due to absence of delocalized electron, that free mobile electron is missing. Why is this one missing? I remember as I was introducing, I told you this, that now carbon from our notes, when I go back here to look at now what we've already discussed, this is what we say, that now between this carbon to this carbon here, we have a strong covalent bond. Between this carbon to this carbon, we have a strong covalent bond. But when you look at this carbon here, this single carbon has been bonded to 4 other carbon atoms. So, having bonded to 4 other carbon atoms, we can say that now this carbon will share its electron with this one, with this one, with this one, with this one. Carbon having 4 valence electron in the outermost energy level, all the 4 valence electron will be used in bonding, and no delocalized or no electron will going to be left delocalized. And because of that one, we can say it is a poor conductor of heat and electricity. So we are saying that now all the 4 carbon atoms, for example, each carbon atom in diamond, carbon atom in diamond is bonded. Each carbon atom in diamond is bonded to 4 other carbon atoms, 4 other carbon atoms, leaving no, hence, or we can say leaving no delocalized electron. This is what we say. And now each carbon atom in diamond is bonded to 4 other carbon atoms, meaning all the 4 valence electron, leaving no delocalized electron. So what am I trying to say this one? Very important thing here. Very important thing here. In B, I want to note this one, that now because each of these carbon atom is bonded to 4 other carbon atom, meaning the 4 valence electron in carbon atom, all of them are used in bonding. So all the four valence electrons are used in bonding. All the 4 valence electrons are used in bonding. So this one important thing that you need to note about this one. Apart from this one, we also say that diamond has a density of 3.51 gram per centimeter cubic. So this is the density of now the diamond, and you need to look at this. Now there's something we said here, that now diamond is one of the shiny crystalline. It's a crystalline that when you polish it shines, and because of this property here, diamond is used in making of jewelries. Now we are going to conclude today's class with actually mentioning some uses of diamond. I'm going to conclude this today's class using some winding up with now the uses of diamond, mentioning some uses of diamond, and I'm going to also tell you the reason as to why it is used for this and not that. So one use of diamond we're going to discuss here, we say that now diamond is very hard, and because of its hardness, diamond is used in drilling and cutting of metals. It's used in drilling and cutting of metals. Why is diamond used as this one? I have some reason behind this. The reason behind now diamond used in cutting and drilling of metals is because of its hardness. So due to its hardness. Then number 2, uses of diamond. We say that now diamond is used in actually making of ornaments and jewelries. It's used in making of ornaments and jewelries. Making of ornaments and jewelries. The reason behind this one, is that it shines when polished. So these are the 2 uses of diamond, and these are some properties of diamond that you need to understand. So class, we can actually look at the second allotrope and discuss their properties and uses in our next class. Shalom. God bless you. Subscribe to my YouTube channel and be ready to learn. I'm your teacher, Mr. Emmanuel Duba. Be blessed.